Chapter 5.4 Equations and Graphs of Trigonometric Functions. Solving trig equations in degrees. Example, determine the solution for the trigonometric equation 4 sine squared x minus 3 equals 0 for theta greater than or equal to 0 degrees and less than or equal to 360 degrees. We'll start by isolating the trig function. Add 3 to both sides. We get 4 sine squared x equals 3. Divide both sides by 4. We get sine squared x equals 3 over 4. Square root both sides. We don't know if sine started as positive or negative before it was squared, so plus minus square root. Then we get sine x equals plus minus square root of 3 over the square root of 4 is 2. And we should recognize this as one of the side lengths in our special triangles. You can either draw the special triangle or draw the first quadrant of the unit circle, which is what I'm going to do. Our smallest special angle is 30 degrees. Next one is 45 degrees. And the next one is 60 degrees. The point on the unit circle at 30 degrees, the y value is 1/2, so the x value is root 3 over 2. For 45 degrees, the two values are the same, root 2 over 2, root 2 over 2. And then for the point at 60 degrees, it's the opposite of the point at 30 degrees, so this time it's x is 1/2 and y is root 3 over 2. And if we recall, sine is the y value of points on the unit circle. So which of our special angles has a y value of root 3 over 2 when the terminal arm meets the unit circle? That would be 60 degrees. So sine of 60 degrees equals root 3 over 2. So our reference angle, theta r, equals 60 degrees for this question. Then we want to use the cast rule to decide which quadrants our solutions are going to be in. Here we have sine x is positive and negative. So by the cast rule, C-A-S-T, obviously, since sine is both positive and negative, we would have solutions in all of those quadrants. In the first quadrant, our answer x is going to equal our reference angle, theta r. In the second quadrant, x equals 180 degrees minus theta r, which is 180 degrees minus 60 degrees, which is 120 degrees. In the third quadrant, x equals 180 degrees plus theta r, which is 180 degrees plus 60 degrees, which is 240 degrees. And in the fourth quadrant, x equals 360 degrees minus theta r, which is 360 degrees minus 60 degrees, which gives us 300 degrees. Therefore, our four solutions for x greater than or equal to 0 degrees and less than or equal to 360 degrees are 60 degrees in quadrant 1, 120 degrees in quadrant 2, 240 degrees in quadrant 3, and 300 degrees in quadrant 4. Solving trig equations in radians. Determine the general solution for the trigonometric equation 10 equals 6 sine pi over 4x plus 8. Let's start by isolating the trig function. We're going to subtract 8 from both sides. We get 2 equals 6 sine pi over 4x. Next, divide by 6. We get 1 over 3 equals sine pi over 4x. Let's let theta equal pi over 4x. Then we can write 1 over 3 equals sine theta. Then we can solve for our reference angle. 1 over 3 is not a measurement from any of our special triangles, but we can solve for our reference angle. Theta r equals sine inverse 1 over 3. Bring up our calculator. We need to make sure we're in the correct mode. I need to be in radians for this question. I am in radians, so that's good. Hit exit, then second sign for sine inverse, and then fraction 1 over 3. And we get our reference angle theta r equals 0.3398 ... This is positive. So sine is positive, which means in our cast rule, we would have solutions in quadrant 1 and in quadrant 2. In quadrant 1, theta equals the reference angle, theta r. In quadrant 2, theta equals pi minus the reference angle. Let's calculate those. Quadrant 1, theta equals theta r, which is 0.3398 ... And in quadrant 2, theta equals pi minus theta r, the reference angle, which is pi minus 0.3398 ... And we can calculate that. Second pi minus second answer gives us 2.8017 ... Question is asking for the general solutions. We can now write the general solutions in terms of theta. Solutions in quadrant 1 would be theta equals 0.3398 ... plus 2 pi n, where n is an element of the integers. And then in quadrant 2, our general solution would be theta equals the solution we just got, which was 2.8017 ... plus 2 pi n, where n is an element of the integers. But remember that our question didn't have theta. Our question had pi over 4x, and we said let's call that theta. So now we need to change that back to pi over 4x. But theta equals pi over 4x. So our general solutions then become pi over 4x equals 0.3398 0.3398 ... plus 2 pi n, where n is an element of the integers, and pi over 4x equals 2.8017 ... plus 2 pi n, where n is an element of the integers. We want to solve for x, so we need to multiply both sides by the reciprocal of pi over 4, which would be 4 over pi, so times 4 over pi on this side, and times 4 over pi on this side. And do the same thing for the second one, 4 over pi, and times 4 over pi. So when we do that, we divide out our 4s and divide out our pi's. We're left with x on the left side of the equal sign. Then when we multiply 4 pi into these brackets, it multiplies to both terms. So to that, and also to the 2 pi n term. So in my calculator, I want to take our first solution, 0.3398. I'm going to calculate that again. So second sine fraction 1 over 3. And then I'm going to multiply that by the fraction 4 over pi to get 0.4326 ... plus 2 pi n times 4 over pi would give us 8 pi n over pi. Then the pi's divide out, and then n is an element of the integers. So this solution would be x equals 0.4326 plus 8n, where n is an element of the integers. In our second general solution, 4's divide out, pi's divide out, multiply 4 pi into the brackets, multiply to each term, which is the 2.8017 and the 2 pi n. Then we get x equals, we want the 2.8017. To get that, we did pi minus our first answer, so pi minus sine inverse of the fraction 1 over 3. We're taking that answer and multiplying it by 4 over pi. To get 3.5673. ... And then 2 pi n times 4 over pi is 8 pi n over pi. The pi's divide out, and then we have n is an element of the integers. So this simplifies to the second portion of our general solution, which is x equals 3.5673 ... plus 8n, where n is an element of the integers. Solving trig equations graphically. Sketch the graph of y equals 6 cos 4x. There's no horizontal or vertical shift here. We just have a vertical stretch and a horizontal stretch. The vertical stretch, remember the a value, absolute value of a is the amplitude. So our amplitude equals 6. And since there's no vertical translation, no vertical shift, our midline is at the x-axis. So the maximum value would be 6. That's our max, and our min would be -6. Next, let's figure out the period. We're in radians, so period is 2 pi divided by absolute value of b. In this case, b is 4, so 2 pi divided by absolute value of 4 is 4. And we can simplify that to be pi over 2, which is our period. So we complete one full cycle in pi over 2 radians. Pi over 2 is here. This is a cos function with no horizontal or vertical shift. Cos functions start with a maximum at the y-intercept. So our maximum of 6 will be on the y-intercept. And then when we complete a full cycle, which is at pi over 2, we'll get back to another maximum at y equals 6. Then we can use our pattern, so halfway between the two maximums, we need to be at a minimum. We have 1, 2, 3, 4, 5, 6 steps between the two maximums. So at 1, 2, 3, I would go down to my midline and put my minimum value here between pi over 6 and pi over 3. We have a max at 0 radians. We have a min on this line here, which we can determine. So if 2 units is pi over 6, then 1 unit would have to be half of that, which is pi over 12. That would be pi over 12. Then 2 pi over 12, 3 pi over 12, which reduces to pi over 4. 4 pi over 12, 5 pi over 12, 6 pi over 12, which reduces to pi over 2, 7 pi over 12, eight pi over 12 reduces to 2 pi over 3, 9 pi over 12 reduces to 3 pi over 4. 10 pi over 12 reduces to 5 pi over 6, and then we have 11 pi over 12. And then lastly, we would have 12 pi over 12, which reduces to pi. So we have a maximum at 0 radians, and we have a minimum at pi over 4 radians. Halfway in between those, which would be here, we're going to have a value on a point on the midline, which is an x-intercept in this case. And then same thing for the other max. Halfway between the minimum, which is at pi over 4, and the maximum, which is at pi over 2, we would have an x-intercept in this case. So halfway between, go down to the midline, put a point on the midline, which is right there between pi over 3 and 5 pi over 12. And then we can join those points to get one full cycle. Then we can repeat this process for our next cycle. So each time I moved over 1.5 on the x-axis. So I'm starting from a max, I'm going to move over 1.5 and come down to the midline and put a point there between 7 pi over 12 and 2 pi over 3. Then I'm going to move over 1.5 units on the x-axis and go down to the minimum. move over 1.5 units on the x-axis, and then go back up to the midline, which is the x-axis. And then again, move over 1.5 on the x-axis and go back up to the maximum. And connect those points to draw another cycle. And that's the graph of our function y equals 6 cos 4x. Part A used the graph to solve the equation 6 cos 4x equals 6 for x between 0 and pi. When is our function equal to 6? That would be here when x equals 0, here when x is pi over 2, and here when x is pi. Part B read a general solution to 6 cos 4x equals 6. So from part A, it was 0, pi over 2, pi. So every pi over 2 starting at 0. So we could write x equals 0 plus pi over 2n, where n is an element of the integers. Or we don't need to write the 0 part. We can write x equals pi over 2n, where n is an element of the integers. Either one of those. Part C used this graph to solve the equation 6 cos 4x equals 3 for x greater than equal to 0, less than equal to pi as an exact value. Let's draw a dotted line at y equals 3. This is pretty challenging to do using a graph that we've drawn ourselves because it's pretty challenging to get the curve to line up exactly how it should. So typically you'd be asked a question like part C if you were given the graph so that it's drawn perfectly. But if we look, we can see that this point here, this intersection point, looks like it's pretty close to pi over 12. This one looks like it's right on 7 pi over 12. This one looks like it's pretty close to 11 pi over 12. So this one's probably supposed to be 5 pi over 12, and the graph is probably supposed to go through this point, through this point, and this point. Okay, so we can reasonably assume that they're going to be these values, especially because it says give exact values. We have to be able to read the x value for each of these points from our graph. So they would each have to land on one of the lines on the x-axis. Then we can use our calculator to test each of the points that we think are the solutions. So we think that we have pi over 12, 5 pi over 12, 7 pi over 12, and 11 pi over 12. Bring up our calculator. Make sure we're in radian mode. Yes, I'm in radian mode. Our equation is 6 cos 4x, so our first x would be pi over 12, so 4 times the fraction pi over 12. If this equals 3, then we know it's a solution. Yes, it equals 3. So we know one of our solutions. Then we try the next one. I can just go up and edit. Hit enter. I can just edit this one. Instead of pi over 12, we want to try 5 pi over 12. And we get 3 again, so 5 pi over 12 is a solution. The next one we expect is 7 pi over 12. Change the 5 to a 7, and we get 3 again. So 7 pi over 12 is a solution to this equation. And the last one was 11 pi over 12. Change the 7 to an 11, and we get 3 again. So 11 pi over 12. Those are our solutions to this equation for x greater than or equal to 0 and less than or equal to pi. We can use graphs of trig functions to solve trig equations that model periodic problems. These include problems that involve pendulums, pistons in an engine, Ferris wheel motion, blood pressure variations, yearly daylight problems, sound vibrations, and many other natural examples. Example: in some Caribbean countries, the current makes 50 complete cycles each second, and the voltage is modeled by V equals 170 sine 100 pi t. Graph the voltage function in your calculator and draw a sketch below of at least 2 cycles. To know what to make our scale on the x and y axes, we're going to need to know the amplitude and the period. The amplitude is the absolute value of the A value, which in this case is 170. The absolute value of 170 is 170. Since we don't have any vertical shift in this equation, we're going to have a maximum at 170 and a minimum at negative 170. Then if I count by 50, 100, 150, 200, negative 50, negative 100, negative 150, negative 200. That's an appropriate scale for my y-axis. My x-axis, I want to know the period of the function, which is part B. What is the period of current in these countries? Period equals 2 pi in this case, divided by the absolute value of B, which is 2 pi divided by the absolute value of 100 pi, which is 2 pi divided by 100 pi, which equals, pi's divide out, 2 over 100, which is 0.02. So one period occurs every 0.02 on the x-axis, which means to sketch the graph of at least 2 cycles, I only need to go up to 0.04. So let's say that every 4 units on the x-axis is 0.01. 1, 2, 3, 4, 0.02, 1, 2, 3, 4, 0.03, 1, 2, 3, 4, 0.04, 1, 2, 3, 4, 0.05. So then 2 cycles will take up most of our grid here. And then we can plug this into our graphing calculator. When I tried this with my graphing calculator app that I have on the iPad, it just wouldn't graph. It was having issues. So I graphed it on my graphing calculator, and I will insert some pictures of the screens of what it looks like. When you graph this function, if you were to put in a standard window, your screen would either be pretty much all colored, or it might just have weird lines. So I'll show you a picture here of when I graphed mine with a standard window of negative 10 to 10 for x and for y. We don't want the standard window. We want the window that we have just labeled our axes with. So we change our windows. For the x-min, we have 0. For the x-max, we put 0.05. And our x-scale is 0.01. The y-min is negative 200. The y-max is positive 200. And our y-scale is 50. And when that happens, here's a picture of the graph that we get. And we could use our graphing calculator to find the x-intercepts. We could also find them just by using properties of the sine function and the period of this function. For y equals sine x, we have an x-intercept at 0, 0, and then the graph goes up to a maximum to the right of x equals 0. This sine function that we're graphing has no horizontal or vertical shift, so we would still have an x-intercept at the origin. Then, because the a value and b value are both positive, it's moving up as it moves to the right. So it's going the same direction as y equals sine x. We also know that the period of the function is 0.02. We just calculated that for part B, which means that when we get to 0.02, we will get back to an x-intercept and then start our cycle again. And then for sine, in one period, we go up to a max, down through 0, and back up to the x-intercept. So we also have an x-intercept in the middle of a cycle. Then again, we could use our graphing calculator to find the max points, or we can just use the pattern. We know our amplitude is 170, so our max values will be at 170, which is about here. And our minimum is negative 170, which is about here. The sine function from 0, 0 goes up to a max and then comes back down to the x-axis. This function's going the same direction because it has no shift, and a and b are both positive. Then halfway between my first two x-intercepts, I have a point at the max. And halfway between my next two x-intercepts, I have a point at the minimum. Then I can join those points together to get the first cycle. And then continue on either using my calculator to find the x-intercepts, max and mins, or using the pattern. I'm going to use the pattern. I know every 0.01 I have an x-intercept, so my next x-intercept's at 0.03, and then 0.04. I know that halfway between 0.02 and 0.03 there is a maximum, and halfway between 0.03 and 0.04 there's a minimum. Then I can join those points together. And there's two cycles of our function. Part C. What do the scales and axes represent? The x-axis, our equation is v equals 170 sine 100 pi t. So the x-axis, or in this case it's shown as the theta axis, represents the t variable, so the time, And it says the current makes 50 complete cycles each second, so the time is in seconds. And then the y-axis represents our other variable, which is the voltage. Part D, how many times does the voltage reach 110 in the first second? Let's just look at one cycle. So the first cycle here, 110 is about here. Two times in the cycle that it reaches 110. The question tells us that the current makes 50 complete cycles each second. So if it's 2 times per cycle and there's 50 cycles, per second, we would multiply those two numbers together. Which gives us 100 times that the voltage will reach 110 in the first second. The pedals on a bicycle have a maximum height of 30 centimeters above the ground and a minimum distance of 8 centimeters above the ground. Assume a person starts pedaling with the pedal in its lowest position and pedals at a constant rate of 20 cycles per minute. Let's start by highlighting the important information from the question. It tells us that we have a maximum height of 30 centimeters, a minimum distance of 8 centimeters. The person starts pedaling with the pedal in its lowest position and pedals at a constant rate of 20 cycles per minute. What is the period in seconds for this periodic function? Sketch a graph of at least one cycle. Our period is, it tells us we go 20 cycles per minute. Which is 20 cycles in 60 seconds, which is 1 cycle every 3 seconds. Therefore, the period for this function equals 3 seconds. We want to graph at least one cycle, so we want to go up at least to 3 seconds. I'm going to say every line on the x represents 0.5 of a second, so 2 lines would be 1 second, 2 more would be 2 seconds, 2 more would be 3 seconds, 2 more is 4, and 2 more is 5. And the x-axis is time in seconds. The y-axis would be the height of the pedal. And that's in centimeters. The highest the pedal goes is 30 centimeters. So we need to make our scale so that we can go up to 30 on the y-axis. If I count by 5, 10, 15, 20, 25, 30, that gets me there. So 5, 10, 15, 20, 25, and 30. Our max is at 30. And our minimum is at 8, so we'll say that's about here. I need to know the midline to graph the function. I can calculate d by doing d equals max plus min divided by 2, which is 30 plus 8 divided by 2, which is 38 divided by 2, which equals 19. That's about here. The question says the person starts pedaling with the pedal in its lowest position. The lowest position of the pedal is at 8 centimeters. So we start at time 0 with the pedal in the lowest position. Then after 1 cycle, the pedal would return to that same spot. So at 3 seconds, the pedal will be back to the lowest position. Halfway between those 2 points, the pedal would be at its maximum position. So at 1.5 seconds, the pedal will be up at 30 centimeters. Then halfway between the min and the max, the pedal will be at the midline, so right here. And again, halfway between this max and this min, the pedal will be at the midline, so right there. And we can attach these points to get our first cycle. Then we could continue our graph. It was 1.5 seconds to go from a min to a max. So 1.5 seconds would take us to 4.5. We would have a max. And halfway between 3 seconds and 4.5 seconds, we would have a point on our midline, which will be right there. And then we can graph those and so on. Part B, determine an equation for the height of the pedal above the ground as a function of time in seconds. We want to determine A, B, C, and D for this function. We already have D, that was 19, that's our midline. We should recall that there are an infinite number of different equations that we can write to represent a sinusoidal function. So I'm going to make my A and B values positive. Then A equals the amplitude, if A is positive, and the amplitude which equals the max minus the D value, which is 30 minus 19, which gives us 11 for A. I can use the period to find the B value. Period is 2 pi divided by absolute value of B. In this case, the period was 3 seconds. I can write that as 3 over 1, and then cross multiply and divide. That gives us absolute value of B equals 2 pi over 3, and I said that B is positive, so B equals 2 pi over 3. Then I just need to figure out my phase shift, the C value. I can write this function as a sine function or as a cosine function. You can look at the midline of our graph and think of it as the x-axes for the graphs y equals sine x and y equals cos x. If we write this function as a sine function starts with a y-intercept at the midline, and then it heads up from there. This is going in the same direction, but we could say that that point was shifted to the right 0.75 units. This would be 0.75 units. Or if we write this as a cos function, we could talk about this first maximum. Our y equals cos x starts with a maximum as the y-intercept, and then it heads down from there. So this point is going in the same direction. So we could just talk about this being a shift over by 1.5 units to the right. So either c equals 0.75 if we write this as a sine function, or c equals 1.5 if we write this as a cos function. And remember, this is only two of an infinite number of possible equations that we could write. Our y value is h for height equals a is 11 sine bracket b is 2 pi over 3 bracket. Our x is t in this case, minus 0.75 for the sine function, and then plus the d value of 19. And a possible cosine function h equals 11 cos 2 pi over 3 t minus 1.5 this time plus 19. C, use your equation to determine the height of the pedal after 4 seconds. Let's do this for both equations. We should get the same answer because the equations represent the same function. So we have h equals 11 sine 2 pi over 3 times t is 4 minus 0.75 plus 19. Plug that all into our calculator. I need to be in radians, which I am. 11 sine fraction 2 pi over 3 bracket 4 minus 0.75 close bracket, move out of the brackets, plus 19 gives us 24.5. So h equals 24.5. And that was centimeters. This is the height of the pedal. And then we'll do the same, but for our cosine function, h equals 11 cos 2 pi over 3 times 4 minus 1.5, close bracket, plus 19. 11 cos fraction 2 pi over 3 bracket 4 minus 1.5 close bracket, move out of the brackets, plus 19 gives us 24.5. Use your graphing calculator to determine the length of time in seconds to the nearest hundredth that the pedal is at least 25 centimeters above the ground for each cycle. Let's hope this calculator will graph this function. Y equals, clear what you have in there. Graph either one of our functions, they'll graph the same thing. 11 sine fraction 2 pi over 3 bracket x minus 0.75 close bracket, move out of the brackets, plus 19. And then as your y2, graph 25 because we want to know when the pedal is at least 25 centimeters above the ground. So y2 equals 25. And then graph that. Need to change my window. I can try standard. So I need to see higher up. Remember my pedal goes from a height of 8 to 30, so I'm going to go y min 0, y max 30, counting up by fives. And then my x-axis is time, so I don't need to see negatives, so 0 to, one cycle was 3 seconds, so I can go up to maybe 5. I want to know the length of time in seconds that the pedal is at least 25 centimeters above the ground for each cycle. So looking at the first cycle, which goes from the minimum down to this minimum, the pedal is at or above 25 centimeters in this region here. I want to find the intersection point of the two graphs for that first cycle. Second, trace number 5, enter, enter, enter. My x value, x1 is 1.025. Repeat that process, second trace number 5. This time, move your cursor closer to the point you're trying to find, hit enter, move your cursor closer to the point you're trying to find, hit enter, and we get x2 equals 1.975. So then the time that the pedal is above 25 centimeters would be 1.975 minus 1.025. Which is 0.95. Then we can write a statement. In each cycle, the pedal is at least 25 centimeters above the ground. For 0.95 seconds. On a particular afternoon, the tide in Victoria, BC reached a maximum height of 3.0 meters at 2 p.m. and a minimum height of 0.2 meters at 8 p.m. Let's highlight this important information. We have maximum height of 3.0 meters, that's at 2 p.m., and a minimum height of 0.2 meters, which happens at 8 p.m. Our axes are already labeled for us. We have the height in meters and the time in hours. Time goes from 0 to 28. I'm going to say that this is the time in hours after noon. So 0 hours would be 12 o'clock. Then 2 would be 2 o'clock p.m. and 8 would be 8 o'clock p.m. Our maximum height is 3.0 meters. Let's draw a line at our maximum, which would be here, 3.0. Our minimum is 0.2 meters, which is here. We have a maximum at 2 p.m., so at 2 on the x-axis, go up to our max line and put a point. And we have a minimum at 8 p.m., so on our put a point at x equals 8 and y equals 0.2. That would have to be half of a cycle to go from a max to a min. 8 minus 2 equals 6 hours is half a cycle. Then the period would have to be double that, so the period would be 12 hours, which means to go from our first max at 2 p.m. to our second max would be at 2 a.m., so that'd be 12 hours later. 2 plus 12 is 14, so at x equals 14, we will go up to our max and put a point there. Let's determine the midline. D equals max plus min divided by 2, which is 3.0 plus 0.2 divided by 2. 3.2 divided by 2 is 1.6. Find 1.6 on our y-axis. Let's draw the midline. There's 6 hours to between the first max and min, so 3 hours would be halfway in between them. So at 1 to 3 hours after the first max, I'm going to have a point on the midline. And then between the next min and max, again halfway between them, so 3 hours down to the midline, put a point there. I can join my points with a curve. And there's the first cycle. Then I can draw the next cycle. From our last max, we go over 1, 2, 3, and then down to the midline. From that point, we go over 1, 2, 3, and then down to the minimum. From that point, we go over 1, 2, 3, and back up to the midline. From that point, we go over 1, 2, 3, and back up to the max. From that point, over 1, 2, 3, and back down to the midline. And we can join those points together. There's the graph of our function. Part B, write a sine function that represents the height of the tide in Victoria on this day. We need to know the A value, B value, C value, and D value. We already know D, that is 1.6. Let's find the amplitude of the function. Amplitude is the absolute value of A, which equals max minus D, or D minus min. In this case, that is 3.0 minus 1.6, which gives us an amplitude of 1.4. Then if I look at the direction that the graph is going and compare it to y equals sine x, for y equals sine x, we have a midpoint at the y-intercept. So let's say that this point started as the y-intercept of y equals sine x. Then it would have been shifted horizontally to get here. But when we think of y equals sine x, from the y-intercept, which is at the midline, it then heads upward as it goes to the right, whereas this one is heading downward as it goes to the right. So we can represent this with a vertical reflection, so by saying that A is negative. So our amplitude is 1.4, and if A is negative, then A is negative 1.4. To find the value of B, let's use the period. Period equals 2 pi divided by the absolute value of B. The period in this case is 12 hours. We can write that as 12 over 1. Cross multiply and divide. We get absolute value of B equals 2 pi over 12, which equals pi over 6. Then we have to decide if B is positive or negative. Y equals sine x would head up from this point. We reflected it vertically, so now it heads down from this point. If we also reflected it horizontally, then this portion would now be over here, so it would be heading up again. So since we have A equals negative in this case, then B is going to be positive pi over 6. And then our C value, we said that this point started as the y-intercept and got shifted over. How far did it get shifted horizontally? That is 5 hours right there, so C is 5. Then we have the function y, which is the height, equals A negative 1.4. It's a sine function, bracket b pi over 6, bracket x, which is t, minus c, which is 5, close bracket, and then plus d, which is 1.6. Part C, write a cosine function that represents the height of the tide in Victoria on this day. So same as part B, just with a cosine function. Cosine starts with a maximum at the y-intercept, so I'm going to say that this maximum started at the y-intercept, which means it was horizontally shifted over 2 in this case. And y equals cos x from that first maximum then heads downward, obviously, since it's a maximum. And this heads in the same direction, so that tells us that both a and b are positive. Then a is positive 1.4 in this case, b is still pi over 6. C, we shifted over 2 this time, and D is still 1.6. Then our cos function is h equals positive 1.4 cos, bracket pi over 6, bracket t minus 2, close bracket, plus 1.6. D over what domain is the function valid? If we think about time in general, time has to be greater than or equal to 0. T such that t is greater than or equal to 0, and t is an element of the real numbers. But if we think more specifically about this question, the question says, on a particular afternoon, the tide in Victoria, BC reached a maximum height of 3.0 meters at 2 p.m. and a minimum height of 0.2 meters at 8 p.m. So it's specifically talking about one afternoon, and the tide changes from day to day. It's not exactly the same every single day. So maybe we say that this is only valid for the rest of this particular day. So t such that 0 less than or equal to t is less than or equal to 12, TER. This would take us from noon to midnight on this particular day. That brings us to the end of the Chapter 5 notes.